Hello, this video is to demonstrate a working prototype of Team 28's senior design project, the development of a bodyweight support system for gait training. The goal of this project was to create a system that could provide a constant uplifting force on a patient. When a patient is recovering from injury, born with disability, or learning to walk with prosthetics, whatever the case may be, it is easier to learn to walk under partial weight bearing first, and then apply those biomechanics to a full weight application. Pictured on the slide, you can see our designed prototype. The original beam this was designed for was 10 feet high and 20 feet long. So this is a much smaller scale model. All the components on this beam can be transferred directly to the larger beam, but this smaller I-beam and stand was created just for our testing and design purposes. There are several components on this beam that will be discussed further later in this video. On the bottom middle, you will see a black hanger plate right here. This is where the patient will be suspended from. So if we go to the next slide, you will see a harness that the patient would be secured in, and two straps would go up these hooks and into the two slots of that hanger, providing the upward pulling force on the patient. For our project, we have also purchased a 26-gallon Cobalt Quiet Tech air compressor. The large volume is so when the test is running, the motor is not running. There's enough air capacity in here for the air compressor to maintain a pressure throughout an entire test without having the noise pollution of the motor. Here is the back side of the system. We have the trolley here with the air cylinder below it. On this side we have the entire winch mount with electronics on top, and on this side we have a pulley and another cable hanger here. On the 10-foot beam, this is all high up in the sky, out of sight, out of mind, so that's why these electronics are still exposed. This cable runs along here to support these cables, the air, power, and data cables running to the trolley. This beam is short enough, so those were not needed, but these loops would be here to support the additional hanging cable in the larger application. Here is close-ups of the trolley and air cylinder plate. On the front side here, you will notice two turnbuckles. These allow to adjust the tension in the cable that moves the trolley side to side. Here's an air cylinder powered by the air compressor shown earlier. This in the middle here is a load cell, a scale that measures the amount of force acting on the patient hanging below. And here's the hanger plate from which the patient is suspended. And just for our testing purposes, we have two springs here with a loop so we can test and move it ourselves. We were very limited in our testing abilities due to the COVID-19 crisis. We were not able to fully calibrate the load cell properly, as we need to suspend high amounts of weight from it in order to do that. We also have no access to the biomechanics lab where this would be used. So the best we can do is to get it working on this model. On the back side of this plate, you will see all of the electronics mounted. Here's two valves that control the air flowing into the cylinder. And this is a 3D printed box encasing an Arduino, a relay, breadboard, and several other wires and ports that are used to control the trolley. Here are other important components of the system. On this side we have the winch mount plate, where there is a cable winch system created here, controlled by a servo motor. Like I said before, all the electronics are mounted on top. On the 10-foot beam, they would be up high, out of sight, out of mind. On this side, we have an aluminum plate with a pulley and a steel plate with two clamps and a eye bolt here to support that cable. This pulley just keeps the cable from rubbing on this end of the beam. In order to move the trolley side to side, the cable goes from here, from the trolley, to this spool. Likewise, on the other side, it goes from the other side of the trolley, around the pulley, back to this spool. These two spools are wound in opposite directions, so rotating the winch one way would wind up one side and unwind the other side, allowing the trolley to move to one direction. And in order to move the other direction, this would rotate the other way, winding up the other side and unwinding the opposite side. Video demonstration of that is coming shortly. This here is a swivel rod mechanism that we have designed. This senses the angle at which the plate is hanging from the trolley. Ideally, we want the plate to remain straight vertical, but obviously when a person walks, the plate will move slightly. This detects that angle change and sends a signal back to the winch to adjust the speed of the motor. And here is that in action. As you can see, the motor moves. We have a high quality cable tensioning zip tie in the middle. And you can see it winding up here and unwinding there. And when it moves the other way, it is unwinding off this spool and winding up on this spool. Here is a test showing you from the cylinder perspective how that side-to-side motion works. As I press on one side, it angles the plate to that direction and moves the trolley to correct in order to keep the cylinder straight vertical. Alright, all these mechanics are nice, but how does a researcher interact with our system? Here I 3D printed a user interface case, which inside holds an Arduino Mega, the touchscreen, keypad, and several other electronic components. 3D printed into it were also accesses for all the ports, power going through to the system, and an Ethernet cable used for data and power transmission as well. So here, first up, when the system first turns on, it'll show you a nice little credit screen with all of our acknowledgments and team members' names. And then I'll bring you to a system adjustment menu. From here, you can manually move the system up, down, left, right, shown in this video. Also from this menu, you can start a system automated test. So here in this example, I will enter 3.5 pounds. Enter, and this will bring you to a safety screen. Are you sure you want to start the test with 3.5 pounds? Yes, you do. And then here on this screen, it tells you the actual weight that's acting on the load cell, along with the target weight, and it graphs the actual weight. Since this is a very low weight, the graph's really low to the bottom and hard to see, but you can see it moving up slightly when I apply some weight to it. When the graph reaches the end of the screen, it goes back to the beginning of the screen, erasing the previous line, and draws over the top of it. To better see the graphing, let me enter a higher weight of 25 pounds. Here you can see, as I apply the weight, it is easier to see the line because it's not so close to the bottom. And exit and power down the system. Here you can see a video demonstration of the automated test in action. As I pull down, the air cylinder moves down. As I rise up, the air cylinder moves up. If I move to the left, the trolley moves to the left, and if I move to the right, the trolley moves to the right. The up and down movement tries to apply a constant tension to the patient below. Meanwhile, the left to right motion keeps the trolley directly above the patient, preventing the patient from having to pull the trolley along the I-beam. Here's the measure results that we have collected. I created new Arduino sketch that goes onto the back of the air cylinder Arduino to provide the actual data points that the load cell is reading. This is a little more detailed version of the graph that's on the user interface that you saw earlier. Running a test with a target weight of 4 pounds, this was the results. As you can see, there is some jump and some zigzag in the collected data. However, if you think about a 200 person on the beam, 1% of their body weight is 2 pounds. So this entire 2 pound range is only 1% of their entire body weight, which theoretically they should barely be able to feel a difference in walking. Some of these improvements can be done with further research. One of the biggest problems that we ran into was our valves are either on or off. There is no controlling that. So by the time we set a threshold, in order to change the valves on or off in their position, it jumps, and there is no slow, gradual changing of pace. But for future research, that is definitely something that can be improved on. And that is a summary of our system. Thank you for watching.